Okay, so last up in this long introductory chapter, we got series. So the definition of a series. Actually, let's talk about this little blurb here quick. So if we were to take a summation, so what we just did, and extend the upper bound, so if we had our summation form right here, we've got our lower bound, we'll say 0, and if we extend our upper bound, so our n, to infinity, the result would be what we call a series. So we're taking the sum from the beginning term all the way through however many terms there are. So this is kind of creating a sort of generalizing the pattern of the function as we get closer and closer to infinity. So another thing to note is that a series follows all of the same rules of the sequence and can be compiled like a sum. So like I had y'all, or I'll have y'all try out what the difference between a series and a sequence is, and you'll be able to find that in here. So let's go over the definition of a series. Consider the infinite sequence A1, A2, A3, dot, 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 A to the I, and dot, 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 so on and so forth. If we have a series like this, then we know two things. We know that the sum of the first n terms of the sequence is called a finite series because we have a finite set of numbers that we're combining together. Or it's called the nth partial sum of the sequence and is denoted by, I'll draw us a little sigma again, and this is what we already know. It goes from the first term to the nth term, and then it ends there. No more terms are counted. There's a finite set of numbers that we're adding together to find the nth partial sum, or the finite series, sorry. And so, on the other side, the sum of all of the terms of the infinite sequence is called an infinite series, and is denoted by all the terms plus a, So what this really is saying on the left side of the equations, or of the equal sign here, is all of the terms in the sequence being added together. And they got the dot, dot, dot on this side, got the dot, dot, dot on this side, which represents the continuity of it. And our sigma in this is going to be similar to that one. So we've got I equals 1 on the bottom, infinity on the top, because that's the term that's our upper limit per se, but we can't actually get there. So that's what we're going to be trying to approach in our sequence. And then we've got A sub I. So that got a little wordy, a lot of information, but it's pretty easy to see in action. So let's go with this example here. I'll just go through this whole thing. We'll find the third partial sum of this right here. So third partial sum means we're going from the first term to the third term. So I'll write our notation over here, our summation notation. Third term is our upper limit. Our lower limit is the first term, because that's what it says right there. And our function is 3 over 10 to the I. It might look like 10 times I, but it's 10 with I in the exponent. So let's go through and find the first three terms of this sequence. A1, A2, A3. A1 is 3 over 10. A2 is 3 over 100. And A3 is 3 over 1000. So A1 equals 0.3. A2 equals 0.03, A3 equals 0.003, and just like we've been doing, since we're taking the sum, we're going to add all these together. And we're going to get 0.333, and that's going to be the third partial sum. But now let's notice, if we were to continue this pattern, and we were to continue finding a to the 4, a to the 5, a to the 6, a to the 7, we would keep going and going and going and going and going, adding 3's, right? And so that's when this infinite sequence comes, or infinite series comes into play, with our upper limit being infinity, lower limit being 1. in our function 3 over 10 to the I, this is going to equal, you'll see if we continue this pattern, it would equal 0.3 repeating, or 1 over 3. So that's how we can use infinite sums and finite sums, and this is how they differ. So thanks for sticking with me through this whole chapter. We'll clear this up next class and bring any questions that you have, and I'll see you then.